just start recording. And here we go. Okay, so it's going to depend on how it's drawn. So if it's drawn, if you have a ring that's drawn flat, but you have, say you have a chlorine here, and then an iodine here. And I interpret that the chlorine and the iodine are coming at me. So to me, this is an up, up. Okay. But then when you go to the ring, you just have to pick whichever carbon you want to start with. So I mean, I always start with this carbon, but that's just because this is the direction of the chair that I draw the best. And I just start here, but you don't have to. But I'm going to make it the iodine. But in order for it to be up, since this is like a pointing down carbon, it has to be equatorial up. And then move around 3, 1, 2, 3. This is also a down, so it would have to be equatorial up. So these tell you direction, but they don't tell you axial or equatorial. You only get that information once you put it on a ring. I mean, on the chair.
Makes sense.
Okay. Okay. All right. Let's see how many are here. Okay, we're about 13, so we'll get there. We're gonna do. You guys are a little bit ahead from lab, which is great, so that hopefully we'll get through the rest of chapter 4 pretty quickly. So we're kind of in like a 4.11, 4.12, 4.13 areas. And so what we've already covered, let me hide this so you can see more, is we've covered the ring or the chair flips. And we've covered axial positions becoming equatorial and equatorial becoming axial. And then we've also covered up stays up and down stays down. Okay. So what we're going to do today, and what we did up here, we just said these were all carbon to carbon and carbon to hydrogen. So just a plain cyclohexane ring. Today, what we're going to do is we're going to talk about monosubstituted rings. And then we're going to finish up with di-substituted rings. Now, the di-substituted rings, in this case, how you have substitution is going to vary. So there's lots of options here, or lots of patterns. And what we're going to spend our time working on is the approach. And if you learn the approach, it'll help working with any of the patterns. If you try to memorize it, it's going to get overwhelming very quickly. Okay. So before we go into the monosubstituted ring, does anybody have any questions about ring flips when all you have is a plain cyclohexane ring? Okay, so different color on here. Okay, so when we have a monosubstituted ring, that just means that one of the hydrogens is absent and there's a different atom in the way, or a different atom in its place. Okay. So when we draw it flat, we're just going to use chlorocyclohexane. Now, when you only have one substituent, it doesn't matter if it's on a dash or a wedge, because dashes and wedges are relative to give the relationship in space between two different heteroatoms. So it doesn't matter if the chlorine is on the top face or the bottom face. It's really not being compared with any other structure or any other substituent. Okay, so when you see them flat like this, you have to put them onto the ring as a chair. Okay. And you just pick whichever one that you like the best in terms of the way that you draw the chair. So again, you start with parallel lines. Okay. Now you can put this chlorine wherever you want. Okay. I typically start with that carbon down here, but you can pick whatever. Okay. So because this is a down carbon, so this is like a peak of a mountain, peak of a mountain, peak of a mountain, and then these three are the valleys. So this is like a down carbon, so I'm just going to put my chlorine down. Okay. You can put it on any other carbon. It doesn't have to be axial. You could put it equatorial if you want to. Okay. Now, since this chlorine is in an axial down position, there is an equatorial up hydrogen. Okay. At room temperature and pressure now, what we have to consider is the placement of equilibrium when this ring does a flip. Okay. So when you say, where is equilibrium? You're asking yourself, which ring is more stable? But you can't determine stability of the ring without knowing the identity of the second ring. So since I'm just going to draw these red arrows on here, and then I'm going to, I'll erase them or these lines. So I had drawn my first set of lines in this direction. So now on this ring, I'm going to draw them in that direction. Okay. Now for this chair flip to happen, this carbon is going to come down. Right, I'd pull this one down, pull this one up. And that would be like on a model kit to get it to flip. Okay, that's not rotating. Like, I'm not saying I'm going to take my ring and do this, rotating. I'm just saying that if I have my ring or my chair, I'm going to pull this one up, this one down. So my other chair will come in this direction. Oops, did that wrong. Okay, so this carbon over here with the big black dot on it, that's this carbon here. This hydrogen was equatorial up, it's now axial up. The chlorine that was axial down now is equatorial down. Okay. Now, when we discuss the equilibrium, we have to consider the various components of strain within these two different conformations. Okay. I'm going to have to erase some of this writing. Okay. So when you have a group, a non-hydrogen group in an axial position. Okay, so looks like this. Okay, and the chlorine is the red. Okay, chlorine is a big atom and it has a very large electron cloud. Okay, and that electron cloud on this chlorine is going to bump the electron cloud from this hydrogen and this hydrogen. Okay, those are axial down hydrogens here and here. Okay. So these are going to interact and these are going to interact. Okay. That interaction, each one, so you'd have one example of it here, a second example of it here. Both of those are called 1,3 diaxial steric strain. So steric strain, remember, is anytime you have atoms trying to share space. So in the axial position, atoms, non-hydrogen atoms, will bump into other groups in axial positions, increasing the value of this strain. The larger this atom is, the higher the value of the strain. So if this had been a fluorine, it would have less steric strain to these hydrogens than chlorine. Chlorine would have a lower value of 1,3 diaxial steric strain than bromine, and bromine would have a lower value of 1,3 diaxial steric strain than iodine. So the size of this group will impact the magnitude of the strain. If this had been a methyl group, CH3, that would still have this steric strain. It would be smaller than if it was ethyl, which is smaller than if it's propyl. So the size of the alkyl chain, as that chain increases, the magnitude of the strain increases. Okay, I'll write that up here in just a minute. Okay, so when you have the ring flip, the chlorine goes out of the axial position and into the equatorial position. Okay. Now the only groups interacting are hydrogens in axial positions, both on the top and on the bottom. Okay. These hydrogens are so small they don't have this steric strain. So allowing the ring flip moves the chlorine from an axial to an equatorial position and relieves or gets rid of this strain. So of these two rings, this ring is more stable, and therefore the equilibrium arrow now would be drawn like this. So there's a higher percentage of molecules in this conformation than in this conformation. 1,3 diaxial steric strain only occurs in groups that are in axial positions. Okay. So the 1,3 diaxial strain occurs when substituents in axial positions bump, and you can, that's just the electron clouds interacting. Oops, that's not how you spell bump either. Bump into other atoms or groups in axial positions. Okay, so the magnitude increases with size. Okay, you don't need to know any of the numbers. Like, you don't need to know the value of this strain. You just need to know that a chlorine to hydrogen has a greater 1,3 diaxial steric strain than a fluorine to a hydrogen. So you can just use size. Are there any questions about that before we look at di-substituted rings. And now with di-substituted rings, we're going to, I'm going to show you why I think it's important for you to learn the approach and not memorize. Okay, so di-substituted rings, if we just draw a ring like this, 1, 2, 3, 4. Okay. So you can have two different substituents. You can have substituents on 1 and 2, or 1 and 3, or 1 and 4. Okay. Not only that, each one of these has a cis and a trans. Cis, trans. Cis, trans. Okay. And each of these has two structures from the ring flip. So this one topic is going to get you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different relationships. If you try to memorize these 12 different relationships, that's a whole lot more work than learning how to do the analysis. Okay. So what we're going to do for our analysis is we're going to take our flat ring, draw it as a chair, and we'll just say chair A. Then flip to chair B. And only after you have those two things drawn, consider the strain. Now, some of the sets are easier than others, but I still think working through the analysis is a better approach. Okay. So we're going to do a couple examples. I'm going to do a couple or one set, and then I'm going to give you a couple practice problems. All right. So. And I'm going to try to split this in half without erasing my own writing. Okay. So the first ring looks like this. Okay. You can name this. These are on the same side. So this is cis 1,2 dimethyl cyclohexane. So you, I mean, obviously, what's going to be over here then is going to be trans 1,2 dimethyl cyclohexane. Okay. Now what I have to do is draw the first ring, whichever one I like the best. This side is smaller than the other side. Okay. Wedges, I'm going to draw as up. So I have to draw on carbons 1 and 2, methyl up and methyl up. Okay, so I'm going to start here. Move this over a little bit. Okay. There's a methyl up. Here's a methyl up. Okay. They're not both, one is equatorial, one is axial, but they're both up on top of the ring. Equilibrium arrow. Draw the other chair. Right. Okay, that's my carbon here, carbon here. Equatorial up becomes axial up. Axial up becomes equatorial up. Okay. Now at this point, you could, if you wanted to, you could put a box around anything that's axial. It could have been on the top of the ring, it could have been on the bottom of the ring. But if you have something in an axial position, it's going to have that 1,3 diaxial steric strain with any of your other axial groups, even if they're hydrogens. So on the left-hand side, you have 2 hydrogen to methyl diaxial steric strains. On the right, you have 2 hydrogen to methyl diaxial steric strains. They're just from different methyls. Okay, so this methyl here is this one here. Okay. But flipping the ring doesn't discriminate or distinguish one as a lower energy conformation than the other. So in this particular case, these are equal energy. Okay. If one of these had been bigger, if this had been a methyl and this had been an ethyl, then it would matter which ring you're talking about. But because these are all the same size, the value of the strain is the same. Now on this side, we do it the same way. We start with our rings. Okay. Now we have trans, which means we have to have them on opposite sides. So one has to be up, the other has to be down. Okay. I like to start with axial positions. I just think it's easier. Okay. Then I ring flip. Let me just put a dot so I don't forget what I'm doing. This one is here. Axial becomes equatorial. Axial becomes equatorial. So if you could go to the participants place on your screen, I'm just going to write a question and then you just answer it yes or no. Is the right ring, right side ring, lower in energy than the left ring? Okay. And you can vote yes or no. We have about 18 people, including myself, and we're at 11 yeses. Okay, so that's right. And that is the correct answer. Yes. Okay. All right. Let's see if I can do this. Let's see if I can. Oh, shoot. Okay. All right. Now what I want you to do I'm going to clear this. All right. All right. Is their steric strain, the 1,3 diaxial steric strain for the left side on the top and the bottom of the ring? Again, this is a yes or no question. If you could vote, please. Okay, good. We're about 10 yeses. And that's also correct. Okay. All right, so the steric strain for the top involves the methyl to those blue hydrogens. The methyl on the bottom has steric strain with the red hydrogens. All of the diaxial steric strain is alleviated when you flip here. So this would be your lowest energy conformation. Okay. All right, so what I want you to do is we're going to do 2 examples. I'm going to let you work on, we'll start with 1 example because you did this in lab, so you're a little bit ahead, which is great. All right, so what I want you to do is take some time. Oops. Okay. And I want you to analyze trans 1-ethyl 3-methyl cyclohexane. Okay. And I want you to determine which of the rings, you draw 2 of them, which of the chairs is going to have the lowest energy conformation. Okay. And then we'll do an example of 1,4, and then we will move on. You're always welcome to ask questions when you're working on these problems on your own. That's fine. It's not going to bother me. Okay, so let's do this one and then you can practice on one more. Okay, so again, you start by drawing the chair. Okay. And then you look at the name. So trans is telling you up and down. Okay, not equatorial and axial, just up and down. Okay. So I'm going to come here and one ethyl, I'm going to put my ethyl group there. Okay. Now you can go 1, 2, 3 in the front if you want to, or you can go 1, 2, 3 in the back. Okay. I always go towards the back, but it's your choice. You can do what makes sense to you. Okay. So down axial, which is an ethyl, up equatorial, which is a methyl. Okay. Flip the ring. Okay. That carbon is this carbon. Okay. Axial down is going to become equatorial down. I'm going to put it out like that because I've run out of some room with my equilibrium arrows. Since I went towards the back to put my methyl, I have to go towards the back. Equatorial up becomes axial up.
I have a quick question.
Sure.
So could we have started with axial up instead of axial down?
Of course.
Oh, okay.
See, the thing is, Jay, this is the ring of the two. To me, this is the easier ring to draw. And so since it's the easier ring for me to draw, and I always use this as carbon 1, and I always go counterclockwise, I tend to make fewer mistakes. Okay. If I had drawn this ring better, and this was my favorite, I would have started here and put the ethyl axial up. It just depends on how you like to do it, but I always like to start on carbon 1 with a down position. And then I adjust how I draw the other substituent and the direction based on the name.
Okay. So
how I do it is not necessarily how you're going to do it versus how the other people in the class are going to do it. The thing that you have to be very careful about is that you don't do things like this. So I had gone like this way to get to my methyl. And over here, to me, this is left to right. This is still left to right. So it's a little confusing. But this is left to right and clockwise. This is counterclockwise. You see what I'm doing? You see what I mean? Like 12 o'clock, 1 o'clock, 2 o'clock, 12 o'clock, 11 o'clock, 10 o'clock, around the clock face. So you have to go in the same direction, but you get to pick the direction you're going in. So if you start here and you go back to get from ethyl to methyl, you have to do the same thing here. Excuse me. And now you moved in this direction, which is still clockwise. Did that make sense, Jay?
Yeah, thanks.
Okay. Now, in these two cases, both of the rings are going to experience diaxial steric strain. You have an ethyl down, which will interact with the 2 hydrogens that are axial down. And on this side, when you have your methyl up, you have your 2 hydrogens that are axial up. But an ethyl group, which is you would draw like this, is larger than a methyl group. So this is going to have higher strain. This is going to have lower strain. The lower strain ring is dominant at equilibrium. Any other questions about this particular example with 1,3 in the trans conformation? Okay. All right. Let's do one more.
Wait.
Yep.
Which one is the most stable out of the two?
This one.
This one?
Mm-hmm. The one on the right, because the methyl is still going to have 1,3 diaxial steric strain. But because this methyl group is smaller than this ethyl group, just if you draw the ethyl group like this, then it's clearly obvious. You see what I'm saying? Like it's closer, so the strain will be higher for a larger group. Even if this thing had flown out, like had gone out here, because you're going to get rotation around that bond. So this end is eventually going to be in the ring.
Okay.
Any other questions? Okay. So now what I want you to do is I want you to try. Oops, I don't want it to be here. Okay. Cis 1-fluoro 4-iodo cyclohexane. Okay. All right, so let's do, I'm gonna do it the opposite way. So in case somebody really likes the left hand or the ring I don't draw well better, then it'll match. Oh. Okay. That looks okay. All right, now, and this goes back to Jay, kind of what you were saying, how do you really know where to start? Now I would start here. And I would just put the fluorine axial up. Okay. And then I'm still going to go in this direction. So this is 1, 2, 3, 4. 1, 2, 3, 4. Okay. And I need an up iodine. Okay. So I have fluorine axial up, iodine equatorial up. Flip. Okay, now in this case, this one got brought down, so now it's here. It was axial up, so it becomes equatorial up. 1, 2, 3, 4, equatorial up, axial up. Okay. Now again, this is a case where you have, in each of the rings, you have groups that are axial. So you're going to get strain here and strain here. But in terms of size, fluorine is smaller than chlorine, which is smaller than bromine, smaller than iodine. So this is going to be higher strain. This is going to be lower strain. The lower strain ring is dominant at equilibrium. So that is the end of chapter 4, and we'll move on into chapter 15 unless anybody has any questions before we move on. Yes, Karen.
I'm wondering about if you have two, what are they called? Substituents
Mm-hmm.
on this, if they're both axial up,
Mm-hmm.
and you're considering steric strain, how would you go about calculating that or figuring?
You would need numbers.
And would you add the two together or multiply them?
Add.
Okay, thanks.
Yeah, so like if this strain fluorine to hydrogen, let's just say that's 3 kilojoules per mole, then this one is 3 kilojoules per mole as well. And then the total contribution would be 6.
Gotcha, thank you.
And then over here, it would be like higher because the iodine is much bigger.
Thanks.
Yep. Anything else? Okay, so 15 is spectroscopy. Infrared spectroscopy and mass spectrometry. I gotta find, oops, where did that folder go? Okay. So very likely we'll get through one today, and then we'll, we might get through both, but I'm gonna have to draw all the spectra freehand, so that'll be a little bit more time consuming. Oops, let's see where your notes start. Okay. All right, so the first part of this, so 15, is infrared spectroscopy. And then the second part is mass spectrometry. And we're going to start with infrared. Okay, now the reason to do any type of spectrometry or spectroscopy is because you can't take a picture like with a camera of a molecule. What you can do is use light to interact with the molecule and see what wavelengths of light are absorbed and which ones are transmitted, what happens to the bonds in the molecule. So you're getting a picture, but it's like an indirect picture of the molecule. So infrared spectroscopy is going to be a way in which you're going to use infrared light to study bond vibrations. Okay. So when you look at light, we're talking about using a specific kind of light. So when you have the electromagnetic radiation spectrum, or the EMR, okay, you have gamma rays. You don't have to memorize this. X-rays, ultraviolet, which would be, this is vacuum ultraviolet. There's two different kinds of ultraviolet, but ultraviolet in the vacuum, this is called near ultraviolet because it's closer to visible, which is here. Then you get infrared, near, infrared, and then microwaves. So we're talking about using the infrared on this portion of the spectrum. As you go in this direction, oops, the frequency, which is given a symbol nu, which is like a fancy little V, the frequency increases. As you go in this direction, the wavelength, or lambda, increases. So they're oppositely related. Okay. When you look at the infrared spectrum, frequency increases right to left, energy increases right to left. Okay. Different types of light cause different types of behaviors in the molecule. So infrared, again, like I said, this affects the bonds. So the most important thing out of this relationship is that energy increases with increases in frequency, decreases in wavelength. Now, unlike Chem 101 and 102, you're not going to have to do any calculations with like the speed of light and any of that stuff, but you should know this basic relationship between the various properties of light. So what we're going to do now is talk about bonds and the energy associated with the bond. So when you have your molecule, it's in traditionally the ground state. And you can, and that just means the lowest energy arrangement of electrons, bonds, all that stuff. Okay. So the ground state is the lowest energy. Okay, but you can have electronic states, you can have rotational states, and you can have vibrational states. So in infrared, what we're going to look at are excited vibrational states. So now on our energy level diagram, when we draw these lines, we're going to say that this is a low energy vibrational state. And these are high energy vibrational states. what's important is the difference here. Okay, so this is the difference in energy between two allowed states or allowed positions. Okay. The difference in energy between the states is related to or proportional to the vibration frequency, the difference in the vibrational frequencies. So if my hands are the bond, okay, bonds will vibrate, okay? How they vibrate is going to depend on whether they're double bonded or single bonded or triple bonded together. So if you have a carbon-carbon single bond, it's going to vibrate slower than if you have a carbon-carbon triple bond, okay? It'll also depend on the weight of the objects. So if I put, I don't know, this eraser now in my hand, my right hand weighs less or weighs more than my left hand, so that'll change the vibration. So a carbon to carbon double bond will vibrate differently than a carbon to oxygen double bond. And that will impact the frequency of the vibration. So when we look at a molecule, we say, well, what does it mean to even have a vibration? So here's an atom, and here's an atom, okay? And they're bonded together, but the bond is a spring. So you can have this bond stretch. So they'll go in and out, in and out, in and out. Okay. If you have 3 atoms, things get a little bit more complicated, because not only do you have the in and out on those springs, but this atom can come in and out, this one can come in and out. Okay, so they would go in, out, in, out, in, out. Okay, that's called a scissoring vibration. Okay. The other way you can have this is that this one comes to you, while this one goes away from you. Okay. That's called a twisting vibration. Okay. Some of these are going to be more important than others, and we're going to talk primarily about the bond spring stretch. Keep losing all my stuff. Here it is. Okay. So the bond spring stretch, or the frequency of the stretch, is determined by something called Hooke's law. Now that's really much more of a physics idea, but what it has to do with is the bond strength and the weight of the atoms. So if we look at 2 different types of bonds, a carbon to hydrogen bond, and compare it to a carbon to oxygen bond. Okay, so in this case, the carbon atoms are the same. And what we're talking about is how this bond, it's not that the atoms are shaking. That's not what they're doing. It's that this bond between them is stretching like a spring. So carbon to a light atom versus carbon to a heavier atom. Because comparatively, oxygen is much heavier than hydrogen. So it is easier to move light things than it is to move heavy things. Okay. So these are high energy vibrations. These are lower energy vibrations. And what that means in terms of your energy level diagram is that you're going to have large differences in energy in the vibrational states for carbon bonded to a light atom versus small differences in energy when carbon is bonded to a heavier atom. So if you can measure a small vibration, you can compare it to a large vibration and you can determine whether or not carbon is bonded to an oxygen in your molecule or if you have carbons bonded to hydrogens in your molecule. You'll be able to identify this bond vibration separate from this bond vibration. Promotion of going from low to high, that's provided by the infrared radiation that you expose your sample to. All right. Are we good so far before we look at some examples and the things to look for in an IR spectrum? Okay, so a traditional IR spectrum. It has a y-axis, and it has an x-axis. The y-axis is percent transmittance. Okay, if you could please go to the participants poll. Does everybody know what I mean by percent transmittance? Okay, most people are, the no's are outweighing the yes, and it's about equal, maybe a few extra no's. Okay, so let's just, I'm just gonna draw it in here and then I'll erase it, okay? So let's say this is your compartment and in your compartment you have a sample, okay? This is called incident light, and the incident light enters the sample or enters the container. The sample is the dots. What comes out is called transmitted light. But let's say our incident light here, we send in red light, blue light, and green light. Okay. And let's say on the transmitted side, only green light comes out. That means your sample absorbed blue, it absorbed red. Okay. So then the green light is going to reach the detector. And the detector will measure the green light and recognize that it's missing blue and red. So in this case, if you say all of the green light reached the detector, then that would be 100% transmittance. If none of the red light or the blue light reached the detector, that would be 0% transmittance. Okay. So this came 100% through, 0% came through, 0% came through in terms of transmittance. If you have 0% transmittance, it means 100% absorption. If you could go to your participants poll, does that make more sense with what transmitted light is? Okay, but now the transmitted light we're talking about is not visible. Like these colors represent visible light. Now we're talking about infrared light, but it's the same general principle. Okay. So percent transmittance is on the y-axis. Something called the wave number is on the x-axis. And the wave number is the frequency with a little squiggly line above it. And what that is it's the speed of light divided by the frequency of the wave. So this is given in inverse centimeters. It's a reciprocal distance. This is just traditionally the way these are done. Okay. The other thing that's weird is that most people view an increase in the x-axis from left to right. But in this case, in IR, this is high wave number, so high energy. This is low wave number, low energy. Now within this area, within this area, then you have a line shape. Okay, so we're going to have to talk about the shape of the line and the intensity and placement of features. Okay, so before we draw anything on here, there are some places for the wave numbers that we have to mark. Okay, so high frequency, the highest energy is 4,000 wave numbers. They typically go down to about 400 wave numbers. So I want you to come here and write 3,000. Here, 2,700. Okay. These aren't going to be to scale, but it doesn't matter. 2,300, 2,100. 1,850, 1,600, and then 1,500. So obviously I'm way off scale. We should make this. There we go. We'll put 400 over here. Okay. All right. 1,500, draw a line up. Everything over here, this is called the fingerprint. Okay, the fingerprint tells you about the backbone of the molecule. All the carbon to carbon single bonds, carbon to nitrogen single bonds, carbon to oxygen single bonds, carbon to halogen single bonds. This portion you're not responsible for. So you can always put an X through anything shown that's less than 1,500 wave numbers. Okay. Now the reason we have these numbers is you have a region of importance right here, a region of importance right here, and you have a region of importance that spreads all the way across here. Now I said that there were single bonds over here, but if you look, these are all single bonds to heavy atoms. Carbon to carbon, carbon to nitrogen, oxygen, halogens. The atom that's missing is the carbon to hydrogen single bond. But because hydrogen is so light and it's easy to vibrate, it's a very high energy vibration. So this is the single bond region when you have some atom bonded to hydrogen, and that could be carbon, nitrogen, or oxygen. This region here is the triple bond region. And you only have in organic molecules carbon to carbon triple bonds and carbon to nitrogen triple bonds. This is the double bond region. You can have carbon to carbon double bonds, carbon to nitrogen double bonds, carbon to oxygen double bonds. So you're looking for features within these regions. Okay, so I hate saying this, but what students do to help remember it is they just write STD across their there's nothing else to say. That's what they write. Okay, this region, the STD, I shouldn't be laughing. STD region, this is called the diagnostic region. Okay, the diagnostic region tells you the functional groups. Okay. All right. Now, some of these features are going to be small. So you might just have something that comes and like you see a point like that. Some are going to come over and they're going to be really big. Okay. That's the intensity of the stretch. So how deep the stretch is depends on the polarity of the bond. The more polar the stretch, or sorry, the more polar the bond, the deeper the stretch. Okay. So you could tell the difference between a carbon to oxygen double bond and a carbon to carbon double bond because this one is polar. And so it'll be a very distinguishing feature between 1850 and 1600. Right, so what we are going to do now is we're going to go into each one of these regions and sort of look at the types of spectra that you're going to see and how to explain some of the regions. So we're going to kind of start here in the single bond region from carbons to hydrogens. Okay, are there any questions about this general thing before we move on? What I would suggest you don't do is memorize like specific numbers. Memorize these regions. So 1600 to 1850 is a place where you can find these bonds. Don't say, well, it has to be at 1710. That's not true because you're going to have some variation depending on the molecule. So it's the regions that are important. And I'll explain why I have an extra mark here. Okay, so I'm going to erase this. And we're going to start with carbon to hydrogen bonds. Okay, these are going to be high energy, high wave number stretches. But what's going to happen is that you have different kinds of hydrogens because you have sp3 carbons, sp2 carbons, and sp carbons. Okay. So what that would mean would be looking at the difference between this bond stretching versus this bond stretching versus this bond stretching. Okay. Now what's interesting is that these three bonds, even though they're all between carbon and hydrogen, they're going to have different stretching frequencies because of how either more locked up or less locked up the carbon is. Okay. So when you have sp3 carbons bonded to hydrogens, these tend to vibrate around 2900 wave numbers. Okay. These vibrate a little bit faster because this carbon is a little bit more tightened up. 3100 wave numbers. Okay. These are even higher still at 3300 about wave numbers. Okay. The reason you see a difference in the stretch is because of the length of the bond. So remember, an sp3 hybrid orbital is longer and skinnier than an sp2 hybrid orbital, which is longer and skinnier than an sp. So those circles are the hydrogens. So you have a longer bond. Here you have a shorter bond. Okay. So you see an increase in the stretching frequency. So I'm going to draw one IR spectra over here that's going to have all of these things drawn on it. Okay, so I'm just going to have this highest energy region. Okay, so percent transmittance. Okay, and then I'm going to have, this is 2700, 3000, and then this will be 4000. And this is wave numbers. Oops, sorry about that. Okay. Now the reason I have the 3000 point on here is that distinguishes right here whether or not you have an alkene or an alkyne. Because if your molecule only has sp3 carbons, you won't see anything higher than about 3000 wave numbers, 2900. Okay. So the feature between 3000 and 2300 always kind of looks like this. Has a lot of like squiggly lines like that. Okay. Anything in this region came from an sp3 carbon bonded to a hydrogen. You're going to see this in a lot of your molecules because a lot of organic molecules have this particular, it's a very common bonding arrangement. Okay. Now, if you like, what you can do is you can always like extrapolate up from 3000 and have a line. Because the alkene sp2 carbon to hydrogen bond is usually right on the other side of 3000. Like that. Okay. So this one, sp2 carbon to hydrogen. Okay. Then if you come back over a little bit farther, you see if you have an alkyne, you're gonna see something like this, and it's real sharp. the sp carbon to hydrogen. Okay. Now it's important to remember that when you have an alkyne, because of the triple bond, this only happens in what are called terminal alkynes. So the alkyne, the triple bond, this has to be the last carbon, and then this is the end, the outside. If the triple bond is on the inside of the molecule, you won't see this feature because there won't be a hydrogen there. Okay. Now, if you don't have one of these features, that's okay. It just means you don't have that functional group. So the presence of a feature is just as important as the absence of that feature. All right, are there any questions about the carbon to hydrogen bonds on an IR spectrum? Okay. We're going to go on to nitrogen to hydrogen bonds. Okay, so these are still high energy, high wave number bonds. Hang on just a second. My kid might have online school today. I have to ask him. Okay, I'm a terrible homeschooler. All right, so nitrogen to hydrogen bonds, these compounds are called amines. That's the functional group. Okay. And you have a couple different, there's two different types of amines that you can have. Right. So you can have an amine where the nitrogen is bonded to two hydrogens, or you can have an amine where the nitrogen is bonded to only one hydrogen. Okay. This is called a primary amine because the nitrogen is bonded to one carbon. Okay. This is called a secondary amine because the nitrogen is bonded to two carbons. Okay. Okay, percent transmittance. Wave number. Okay, so here's 3000. Okay, and if you look, here's an sp3 carbon to hydrogen, here's an sp3 carbon to hydrogen, here's an sp3 carbon to hydrogen. So again, you're gonna very often always have that feature. And here you have 1, 2, 3, 4, 5. Oh man, I just wrote all over my shirt. Damn. sp3 carbon to hydrogens. The difference is going to be on the side higher than 3000. Okay. So in this bond, you have two hydrogens. Okay, so they can either be stretching like this in phase, which is called symmetric, or one can go in and one can go out. That's called asymmetric. So you're going to get a symmetric stretch and an asymmetric stretch. And all that means is that when you come over here, you're going to see like a double thing like that. Whereas over here, you only have one stretch and it looks like this. Okay, so this is a little bit broader, left to right, than a carbon to hydrogen. Okay, this looks like the underside of a female cow. It looks like an udder. So that's how you can tell the difference between the two different types of amines. Because this one only has the one bond, obviously you can only have the symmetric stretch. All right, any questions about the amines?
What type of questions would we have
I'll
about?
show you in just a minute.
Oh, okay, thank you.
Yep. Okay. Let's see. All right, the last ones are that we're going to spend a lot of time on are the oxygen to hydrogen bonds. And these are going to have implications in other areas of the spectrum as well, because you can have oxygen atoms in a lot of different functional groups. Okay. So we're going to look at the oxygen to hydrogen stretch in an alcohol, as well as an oxygen to hydrogen stretch from the carboxylic acid. Okay. So we're going to do the alcohol here and the carboxylic acid over here. And so alcohols would look like this. Carboxylic acids look like this. Okay. So right off the bat, you should see that this is a different COH than this one because you have the presence of that double bond. The carbon to oxygen double bond is very easy to see in the IR. Okay. And I'll show that to you in just a minute as well. Okay, so you have your alcohol and your carboxylic acid. Okay. Percent transmittance, percent. Oops. So this is 3,000, 3,000. And like I said, you're almost always going to have that bit there from the sp3 carbons to hydrogens. Now, alcohols are very easy to distinguish because once you get over past 3,000, you have like this really broad, flat thing. I mean, it's huge. You cannot miss it. It's like a big old fat well. Okay. Now, sometimes what you'll see is the big well, and then you'll see a little thing next to it. Okay. Oftentimes, when you have this and this is still an OH stretch. It looks like an sp carbon to hydrogen, but it's not. Okay, so this is an OH stretch if there are no intermolecular forces. Okay. This is the OH stretch with intermolecular forces. This is the one that you have to be able to recognize, not this little sharp one, this one. Other thing to note is that I drew this alcohol stretch in the same region that you would see an amine stretch, either a primary or a secondary nitrogen bonded to hydrogen. So I can't ask you to determine whether or not this molecule also has a nitrogen because you can't see it under here. So we're talking about being able to distinguish one functional group from another, not seeing whether or not you have necessarily multiple functional groups in a single molecule. Okay, so this is smooth and broad. Okay. When you have a carboxylic acid, this OH stretch gets shifted. Okay, so I'm going to have to redraw this because I forgot I need another region. So this part, this broad OH stretch, is still going to be in here. But because of the presence of the carbonyl, the other portion of this functional group, it gets shifted to the lower energy side so that these two features end up overlapping. So your big, broad alcohol stretch or OH stretch ends up interacting with your sp3 carbon to hydrogen stretch. Okay, so you get your OH and sp3 carbon to hydrogen. So this is still broad, but it's kind of jagged. So broad and smooth with a separation is an alcohol. Broad and jagged with no separation is a carboxylic acid. The other portion of the carboxylic acid is that carbonyl carbon double bond oxygen, and that's going to be in that 1850 to 1600 region. And carbon to oxygen double bonds, like you literally can't miss them. They come almost all the way down, and they're almost like 100% transmittance. That's C double bond O. Okay, now this feature, carbon double bond oxygen, this feature would be in a ketone and it would be in an aldehyde. But in a ketone and an aldehyde, you don't have an OH. So then this part would be gone. I'm going to try to share my lecture, like the PDF of the lecture notes with you, and then show you a couple things about how this would be, how these questions would be asked. Let's see, okay, can you guys see like my internet browser?
Yeah.
Okay, let's see. Okay. See, we'll come back to this one. All right. No. Okay. Oh, okay, I don't have it in there. All right, but if you go back up, like these are just prettier pictures of what I just drew. So this is things that we have in your slides. So it's important, like this is a nut called a cyano group. And then an alkyne, an alkene, this carbon to nitrogen double bond, and then this carbon to oxygen double bond, like I said, is in ketones, aldehydes, esters. So it's really just putting the pieces together to build the functional group. So if we go down here, all right, this is the sort of thing that like you should be able to do by Monday. Okay, so it's basically asking you, if you see this infrared spectrum, what is the functional group of the molecule? Okay, so it doesn't tell you, I'm going to type on here real quick. Okay, so the IR doesn't tell you the molecular formula or the molecular mass. The diagnostic region only tells you which functional groups are present in the molecule. Okay. If you want the mass, you need the mass spectrum, which will be the second part. That'll be the spectroscopy part from tomorrow. Okay. So you get your infrared spectrum, and the first thing that I would do would be to come over, oops, draw a line, thick line, at, so 1,000, then you'd have to be able to infer that if there are this many tick marks between 1,000 and 2,000, that they each represent 100. So 1,100, 1,200, 1,300, 1,400, 1,500. So I'd come up and I'd draw a big line here and say that what's going on over here is the fingerprint, which you can ignore. Okay. Then I would come in and I would do the STD on your y-axis. So I would say, okay, 3,000, 29, 28, 27, 23 to 21, 1850 to 1,600. Okay. All right. Single, triple, double. Now you got to be flexible here, okay? Because you could come up and be like, what is this teeny tiny little bump right here? It's nothing, it's background noise. So in infrared spectrometer, when you do this analysis, you have to flush out all of the water and all of the carbon monoxide or carbon dioxide in the atmosphere to get everything out of that chamber so that you have as little background molecules vibrating as possible. But every now and then you're going to get a stray something or other in there. So there is going to be background noise. So you have to kind of say, I think I can ignore that. Okay. Then you come back and you find the region where you can separate the different types of carbons or the different heteroatoms from the carbon sp3 to hydrogen stretches. Okay. Now here you have that kind of jaggedy looking thing to the left of 3,000. So this thing are all of the sp3 carbons that are bonded to hydrogens in the molecule. Okay. Then you look to the high energy side and you see this big, smooth, broad feature that also has a little jaggedy side. Now, because this is smooth and broad, you would say that that's an OH from an alcohol participating in intermolecular forces with either the solvent or other alcohol molecules in your system. And this feature is likely hydroxides, OHs from alcohols that are not participating in intermolecular forces. So even though you don't know what kind of alcohol this is, you can say at the end of this analysis that this IR belongs to an alcohol. I can't remember who asked me about how things were going to be asked, but does that make sense? Like you'd see a spectrum and you'd be asked what the functional group is.
Yes, that makes sense. And those would be just like multiple choice options, so like alcohol.
Well, your whole exam is going to be multiple choice options.
Okay.
So because of the way, and we'll talk about that tomorrow. I'm going to talk to Dr., or if not, you'll get an email from me on Saturday, but Dr. Barrios and I are going to start talking about the exam. It's going to be all multiple choice. So there's two ways to ask the question. Either you see the spectrum and you have to select either a molecule that has the correct functional group or the name of the functional group. Or you could be asked, which of the following IR spectra could be a ketone. And then you would pick from 4 of which of those 4 could belong to a ketone based on what you see. That's kind of just off the top of my head, like how multiple choice could be asked, unless it was like just a word problem. Like, what is the point of using IR spectroscopy? A, determine the functional group of the molecule. B, determine the mass of the molecule. C, determine the relative placement of the carbon atoms. You see what I'm saying? So there's a couple different ways that they can be asked, but what you should, and I'll show you this on the, in just like, I've got one more like that we'll do together analysis like this, and then I'll show you how I would approach learning these spectra. The best advice I have for you with these is to, and I can show you these at some point, like, because I've got them at my house. So I have 2 kids, okay? And they look a little bit alike, but they don't look a lot alike. But I have pictures of them from various ages throughout the house. So if you saw a picture of one of my sons, you could find him in other pictures, even though they're slightly different because of age differences. So when you approach these, it's like, I mean, I'm a terrible surfer, but you kind of have to approach it like, you surf with straight legs and you don't have your knees bent, you're going to fall, because you have to be able to adjust to slight differences in the way the waves are coming in. Okay, you have to be able to adjust to slight variations. Like, what if this alcohol had been deeper or fatter? It doesn't matter, it's still just an alcohol. Okay, so let's do another one, and then I'll show you some examples, where a file is with more examples. Okay, so clear measurements. Oops. Okay, so what is the functional group of this molecule? Okay, now again, I would start in the exact same way every time. Come in and find 1500, so 10, or sorry, 1000, 11, 12, 13, 14, 15. And come up. Okay. Then I would come over to 3000. Come up. Okay, now this one isn't given as percent transmittance, it's just transmittance. So this thing, it's the baseline up here is like 90% transmittance. So there's only like 10% of something contributing to this, which is probably in the background. So this feature up here you can ignore. But what you learn in this region is that there's nothing significant here. Okay, so if you can say that, you know you don't have an alkene, you don't have an alkyne, you don't have an amine, and you don't have an alcohol, and you don't have a carboxylic acid. Because all of those functional groups have to have something greater than 3000 wave numbers. So the fact that there's nothing there actually gives you a lot of information. Okay. Then you see this feature here. Oh, golly, that's ridiculous. It's still ridiculous. Maybe it's, oh, it's too broad. Sorry. This one right here, that is your sp3 carbons to hydrogens, which again are very characteristic. And I should have done my STD highlighting earlier. So here's the single, triple, double. So we've already dealt with the single bond region. Now you look in the triple bond region. That's background. There's nothing significant. And you come over to the double bond region and you see this massive peak that goes the entire length of the y-axis. Okay, the more intense and deep this feature is, the more polar the bond that's being excited has to be. And the most polar double bond you have is the carbon to oxygen double bond. Okay. So then you would consider which functional groups have carbon to oxygen double bonds. Okay. You could say ketones are in. Aldehyde is in. Ester is in. Okay. Now, ethers are out because they have carbon to oxygen single bonds. Okay. So we're not going to have IR of any sulfur containing groups. So it's really the things that contain nitrogens, oxygens, and carbons that you really have to worry about. Okay. So any of these answers, ketone, aldehyde, or ester, would be correct at this point. If you had been told previously that this compound contains only a single oxygen atom, then the ester would be out because esters have 2 oxygens. Are there questions about this one before I show you a file of examples and then some suggestions on how to go about studying it? And then we'll learn mass spec tomorrow and start chapter 5. Monday will be a little bit of chapter 5 and a little bit of a review for the exam, which will be Monday afternoon. Okay, so let me clear this. Okay, so if you go into, oops, okay, the class here, okay, and you go into my notes, the slides, and you come down, you see practice IR problems. I would download them, and I actually would print them. And then I would cut the pictures in half. So I got all of my, all of these spectra came from the NIST webbook. So you could go to the NIST webbook if you wanted to and look up a bunch more. Okay. And then just, you have 2 pictures. Okay, so I would cut this out and I would write alcohol on one side and put this IR spectrum on the other. Okay, you might want to do it twice and have it like a memory game. Okay, it doesn't matter that I put this on here because I wanted to make sure that I had credit for the NIST website. So this is the NIST webbook image IR spectrum of isopropanol. But it doesn't matter that it's isopropanol, you can just write alcohol. Okay. Here's an example of a carboxylic acid. So you see that jaggedy OH peak, and you see a big long carbonyl C double bond O. Okay. Here's a ketone, C double bond O. Here's an aldehyde, C double bond O. Now there are differences. If you look right here, there are differences in the ketone versus the aldehyde based on the presence of this hydrogen. But I'll ask Dr. Barrios Sosa. We typically don't ask students to distinguish aldehydes from ketones. Here's a plain old alkane. An alkyne, so you have a terminal alkyne. So this bond here is, this one right here is the carbon, sp carbon to hydrogen stretch. That's this thing right here. And then I have an alkene and then an amine. So amine, see, like it's pretty broad. This is kind of a messy one, but it's not smooth like the alcohol peak. So I would print these out and make flashcards and just keep looking at functional group name, functional group picture, functional group name, functional group picture. And that will help significantly. All right, are there any questions before we end for today? Okay, so I will put these slides up as soon as I get them from Zoom, which should be, in an hour or two. And then today's Thursday, so we'll meet tomorrow, and then we'll be in good shape. All right, if there aren't any other questions, I will see you guys tomorrow. Have a good rest of your day. I know what you'll be doing. Studying.
Bye. Have a good day.
Thanks, you too.
Thank you very much. Have a good day.
You're welcome. You as well.